Hello everyone. Last presentation of the HUG. So as Willie said, Alexander and Matt worked with me on this, but I'll try to do all the talking and they can jump in as needed. So this talk is really about a bunch of possible projects we could do to enable HDF5 for the cloud. I should say upfront that none of these are work in progress or funded. They are all now just at the idea stage. But one of the things we're hoping to accomplish is to get feedback from the HDF community and see which of these have more interest. Or maybe you have some other ideas that are even better. So with that, let's go on to the next slide. So I'm going to talk about, in general, what's a cloud. I know the cloud has come up several times this week, but I thought it might be good just a baseline, what we mean by cloud. And then cloud storage, and why is it hard to use HDF5 in the cloud currently? And then several different ideas we have to make HDF5 work better in the cloud. And then finally, conclusions, next steps. Next slide. So first, what is the cloud? I would define cloud as on-demand compute and storage, plus other services that the cloud provider may provide, but it's primarily about compute and storage. And the characteristics are pay-per-use. So for example, in the cloud, if you want to use a VM, you don't pay for the cost of that VM forever. You pay for an hour of use or such. Secondly, it's multi-tenant. So when you are connected to let's say an Amazon called EC2 instance, there are quite possibly other customers on that same machine as you. And that can have effects on your performance and I/O throughput and such. But it's a cost-effective way for these companies to service many different customers. Thirdly, it's highly elastic. Typical.
Hello, John. You're breaking up a little.
By contrast, in the cloud, you can say, well, now I just want one machine. And the next hour, I want to have 100 machines. And that's all fine. The scale of these cloud providers is such that there's basically nothing you can do as an individual organization that is going to kind of budge the needle as far as the provider's capacity to serve your request. Another interesting point is that these resources can be managed programmatically. So things like creating a new VM, you don't need.
Hello, John. You're breaking up a little.
Sorry, did I cut out there for a minute?
All right. So perhaps to keep things more consistent, Alexander, can you take over for now?
Yeah, okay. So where we are, you was talking about resources can be managed programmatically, I think.
Right.
Oh, you're back.
Yeah, back. You want me to try to carry on?
Yeah, go over it. Yeah.
Okay. All right, sorry. So the other thing is that resources can be shared with other tenants. So for example, if you create data in a cloud storage, then it's fairly easy to make that data accessible to other users, either the whole world or whatever select accounts you want to share with. Next, the three big cloud vendors are AWS, Azure, and Google Cloud. And they're all fairly equivalent in terms of costs and features. They keep a close eye on each other, and it's very hard for one to create a new feature that the others don't quickly copy. So I'll be talking mainly about AWS, but module some specific details. You can approach Azure and Google in pretty much the same way. Okay, next slide. So that's the cloud. So who cares about the cloud? Why does it matter to us? Well, many public and private organizations are moving their IT to the cloud, either in part or entirely. I mean, shutting down whatever on-prem data center they might have. For example, NASA decided to move to AWS back in 2012. And being NASA, I think it's still an ongoing process, but they've made their direction clear. A second reason is that it can be very cost effective. It can also be very expensive, but in many use cases, there's a big cost savings to using a cloud. If, say, you're using a CPU from 8 a.m. to 5 p.m. every day, then basically you paid for the hardware to sit idle 2/3 of the time. On the cloud, it's easy to scale up resources as you need and scale down when you don't. And since you're only being paid for the time you're using those resources, it's a potential cost savings. Third, there are terabytes or maybe petabytes of HDF5 data freely available in the cloud. And big data has a kind of gravitational black hole thing going on, where because that data is there, it kind of sucks in compute to be close to the data. If there's 10 terabytes of data in the cloud, it's typically much more effective to move your application to that data center versus trying to download all that data locally. On the other hand, HPC workloads have been relatively slow to move to the cloud. And I think that's mainly because of the cloud has been slow to provide things like Slurm in the cloud. And it's less cost effective if you're running, say, thousands of cores continuously compared to paying a cloud vendor for the same capability. Even so, I think it can be of interest for non-MPI workloads, for spike loads, for data sharing, and so on. So I think everyone should pay a little bit of attention to what's going in the cloud, even if that's not their primary focus. Next slide. So I think one of the biggest differences in the cloud for HDF5 users is cloud storage. In the cloud, object storage systems predominate. So on Amazon, this would be S3. Microsoft has Azure Blob. Google has cloud storage. These are all similar in how they work. In that, they're not POSIX. So you can think of it as more of an infinite key value store. There's no limit to how much keys and values you put on the system. But you don't have the typical POSIX primitives, right? You have to custom write or use libraries that provide kind of POSIX equivalent services as much as they can. One critical difference is that in object storage, there's no partial write. So you have a key, you have a value, you can't write pieces of that value. You have to rewrite the entire value each time. So if you had, say, a 4 GB HDF5 file and you wanted to update one attribute, it'd be pretty inefficient, right? To have to rewrite the entire 4 GB file. For read, though, there is a way to do a partial read. It's usually referred to as range get. So it's saying, I want to read from this offset this many bytes in a object. So that's pretty convenient for read-only use cases. And so I think it's a pretty common way where you're creating HDF5 files in a traditional way on a local system, and then pushing those files off to the cloud. So they're write once, read many kind of use cases. The other thing about object storage that makes it so predominant is low cost. So it's 2 cents per gigabyte per month. And if you compare that to systems like EFS, which is sort of NFS in the cloud, it's 10 times that. And that may not matter if your data needs are relatively small, but most HDF users are dealing with large amounts of data, and those costs add up. Another nice characteristic is they're highly durable. So when you write to S3, it gets replicated in two other systems, in two other data centers. So it's very unlikely that you would lose any data that you write to S3 ever. And as I mentioned, once you have data, for example, in S3, it's easy to share that data with other users. But one thing to be aware of is what's called egress cost. So if you have data in S3, you can freely use that data within the AWS data center. But if you try to download the data, there's a cost involved. And I think it's like 3 cents per gigabyte or such. So if I had like a large file and I made it publicly available and it was super popular, then by default, I'd be on the hook for paying the egress costs for all users downloading that data. Amazon does have something called the Public Datasets Program. So if you have a large data collection that might be of interest to the broader public, they can host that data for you for free and pay whatever egress costs are involved. Okay, so next let's talk about performance. The most predominant thing is the latency compared to an attached SSD or even NFS or rotating drive. It's typically like 200 milliseconds per request, which is ginormously more than what you see in an SSD drive. On the flip side, S3 supports a very high request rate, so 5,500 requests per second. And to maximize throughput, you want to make each request read a fairly sizable chunk of data. So 2 to 8 megabytes per request would be best. And lastly, to get the best performance, you don't want to send one request, get some data, send a request, get some data. You want to have like 8 to 16 in-flight requests at any one time. So I say, I want to read 8 range gets, then wait for those to come back, and then do my next step of processing. Next slide. So what's the problem with HDF5 in the cloud? Well, first of all, HDF5 was designed for POSIX storage primarily. So it doesn't work at all out of the box with the S3. Now there's a VFD, which is a low-level driver for library, called the ROS3 VFD that allows read-only access to HDF5 files in S3. For Python, there's also something called FSpec, S3FS, that does a similar function. But performance is limited. And it's limited because all the characteristics I had in that last slide about how to get best performance are typically not followed when you're accessing content through the HDF5 library. So in non-parallel HDF, which is the only one that works with the ROS3 VFD, you will only have one S3 request outstanding at any given time. And things like metadata requests will be typically very small. So you have a lot of small requests serially sent out, and the latency of each of those requests becomes substantial. By contrast, HSDS and ZAR deal with this using the sharded data model. So in this data model, each piece of metadata is a small JSON object, and each chunk is its own object. So rather than having one file, you have potentially millions of these objects that would represent the same content as in an HDF5 file. And this allows them to do things like update a chunk, right? So now you write a chunk is one object, so you're just writing the number of bytes of that chunk, not the entire file. So you could say, why don't we all move to ZAR? Problem is those petabytes of data already in HDF5, right? Transcoding that would be super expensive and time consuming. Another point is that both HSDS and ZAR are relatively immature, and I don't think they have the battle hardening and features of the HDF5 library at this point. So let's talk about various possibilities to improve where we are. So as I was saying, VFDs are library plugins. And what they do is they intercept these IO commands for seek and read and write, and potentially replace it with an alternative implementation. The ROS3 VFD does this by changing those reads to be S3 range gets. So while the library is saying read from this offset this many bytes, the ROS3 VFD is saying do a range get request S3 for this object for this range of bytes. So that very transparently works. It's a relatively simple thing as they go. The bulk of the library doesn't need to change to have this functionality. And you can use it from C or Python. You don't even need to make any programming changes. You can just have environment variables that have the ROS3 VFD automatically invoked. Many of the HDF5 command line tools, though not all, have options to use the S3 VFD. For example, in S3, you may need to pass your AWS credentials to have permission to read a file. All right, next slide. So, question, how does this perform? Well, I mentioned that it can be quite slow because of the serial nature of these requests. And I found, like, compared to HSDS, it can be maybe 40 times slower using the ROS3 VFD. One range get request at a time, slows things down, and you have a sequence of small reads will add up latency. So how can we deal with this? Well, without any changes to the code, you could be good to use larger chunk sizes, right? So each chunk read will, if it's larger, let's say I'm reading a 4 megabyte chunk, that'll be much faster than reading 1,000 1K chunks. Also use the HDF5, which Aleksandar has talked about. And another thing I would say is avoid using variable length types if all possible. Because variable length types, the way they're stored in the file, reading a chunk of variable length types will involve many, many small S3 requests. But again, both of these revolve either changing how you're currently structuring the file or transcoding the file after the fact, which can be negative. So there are actually many ways that the VFD can be enhanced. And I would say that there's nothing that HSDS is doing to read S3 that the VFD couldn't do. So you have, I would say, a potential at least 40x improvement in performance. So what could we do? One is this read-ahead logic. So when the library tells the VFD to read 10 bytes, it might make sense for the VFD to read a megabyte and then keep that extra megabyte around. The next time a data in that range is needed, you can just return it from memory. This often works surprisingly well because metadata bytes tend to be clustered in one part of the file. Chunks that are close in the data space. So if I say I have a one-dimensional data set, I have chunks 0, 1, 2, 3, it often happens that those chunks were written at the same time and they will wind up sequential in the file space. So now if I read, say, 1 4K chunk, but I'm actually reading 4 megabytes, then I would have the next 1,000 chunks already lined up. Another more involved change would be to extend the VFD interface to use selection IO. So if I have a data set and I do a selection of that data set, it's very possible that that selection will hit multiple chunks. Currently, what happens is each of those chunks is read serially. But if instead, the VFD interface says, hey, I need to read these byte ranges from these chunks, and that information is supplied to the VFD, then the VFD would be free to parallelize those requests, right? If the chunks are large or disjoint in the file space, the VFD could have multiple S3 requests going out using some form of async IO. If the chunks, or if the range gets happen to be close in file space, it may make more sense to have one S3 request that reads kind of a superset of the range get request and brings all that in one request. That's what CoH5 does with called intelligent range gets. A third thing would be to support H5D read multi. So Matt talked about this in his talk yesterday. Currently, the non-parallel HDF5 library for the H5D read multi is supported, but its implementation is sequential. For each of the dataset selections, we'll read them one by one. What we could do is to have this parallelize that read so that when you have an H5D read multi, we use the selection IO mechanism to say, I want to read these 10 selections from these 10 data sets. And now on the S3 request, you'll have multiple requests going out to S3. Lastly, enabling multi-thread support. So if the library supported multi-threading, and if the ROS3 VFD supported multi-threading, then your application could spin up multiple threads. And now these IO requests to the library would translate to S3 requests, and this will all happen in parallel. It does require changes in the application code, but there could be a big win there. All right. So next, HSDS. Let me talk a bit about HSDS for people who are not familiar with it. HSDS is a data service for HDF. It's based on a REST API. So all interactions with HSDS are through HTTP requests. This is a very popular concept in the cloud where the services that the cloud vendor supports are not typically libraries, they're services that you interface with through an endpoint and a REST API. HSDS is scalable in the sense that you can configure HSDS to run any number of processes, or if you're running in Kubernetes, even multiple machines. For a swimmer, HSDS is murmur, multi-write, multi-reader. You can have any number of clients to an HSDS service, and those clients can be both reading and writing data at the same time, even to the same data sets. It uses a sharded data store similar to ZAR, and it also has support for reading traditional HDF5 files. This is read-only, and it works through a mechanism where HSDS extracts all the metadata for these files, basically links and attributes, and where each chunk for each data set is located. And then in HSDS, when it needs to read a chunk, it can do the range get to the HDF5 file to get that given chunk. On the client side, in addition to just using the REST API directly, there's H5PyD, which is a H5Py API compatible Python package. The D, by the way, stands for distributed, so H5Py distributed. Then there's the RESTful, which is a vol plugin for the H5 library. And the RESTful, vol is basically a higher level plugin compared to the VFDs that subsumes a more substantial portion of the HDF5 library functionality. Next slide. So here's my favorite schematic. So starting on the right, remember we have this sharded data store. So you have JSON for metadata, you have binary blobs for chunks, and each of these has an ID, and that ID is used to create a virtual partitioning of all the objects that HSDS will be accessing. So this virtual partitioning is indicated by this dashed line in the object store. Secondly, there are things called data nodes. So for each partition, there's exactly one data node. So the data node owns that object, so to speak. So any reads to an object in a given partition are coming through the corresponding data node. Similarly, any writes go through this data node. And this has some advantages. For one, the data node can cache recently accessed objects. So if I said already, if the data node has already seen a recent piece of metadata, it'll keep that in the cache. And if a following request comes in for the metadata, it doesn't need to go to S3. It can just return it directly. For writes, when a write comes in, it doesn't need to immediately write that data. It can do a lazy write. So let's say you have two clients that are both going to update the same chunk. Say client one is updating even rows and client two is updating odd rows. Both those requests can come in more or less simultaneously. The data node will be munging those different writes or toggling, and then at some point in the future, writing it out to S3, where the future is typically 1 second or less since the write. The service nodes are the endpoints that clients talk to. So service nodes do authentication, authorization, validation of the request, and then determining which data node or data nodes are needed to service request. So if during a selection, for example, that crosses many chunks, perhaps all the data nodes will be involved in doing that read or write selection. So we have a degree of parallelism here, right? There's one service node for one request, but multiple data nodes are involved in servicing request. And then finally, the load balancer is a device that can provide one endpoint, but actually service multiple different service nodes behind it. And a client would talk to that endpoint. Okay, next slide. Okay, so the RESTful is good, right? You have your C app using the library. It does need to change its code. It does all the same things it would do with the POSIX file, except now those API calls are getting translated to HTTP requests to HSDS. So what's the problem? If my application is using multi-threading, then it has a certain amount of parallelization, right? So that's represented by this multi-lane highway on the left, right, and the happy face. Similarly, HSDS is multi-process doing multiple things at the same time. But in between, we have this one-lane road that's connecting the two. So my multiple threads in the application are making calls to the library. Those get serialized into one call at a time that go through HSDS. So basically, you're losing all the capability you've had in your application that you seriously converted to multi-threading and in HSDS because you don't have this fast interchange between them. Next slide. So what can we do? Support true concurrency throughout the call stack. So enable multi-threading in the RESTful, which is fairly easy to do because there's little code in the RESTful that relies on coordination between multiple threads. Secondly, all the packages above the RESTful need support multi-threading like H5E, H5S, H5T, and so on. The result is that multi-threading apps will amortize the service latency. So compared to writing to POSIX, your application has more latency talking to HSDS. But if I'm free to use multiple threads, then I can basically keep the network pipe full and get overall high throughput despite the higher latency. Okay, next slide. Okay, our next idea is HDS ZAR storage. So we talked a bit about ZAR this week. So HSDS has its own storage schema that were coincidentally developed at roughly the same time. So they're both sharded storage. They're both use metadata as JSON files. There are some differences. The HDS schema supports multi-linking, i.e. you can have a data set that has links from two different groups. There's various HDF5 subfeatures are supported in the HDS schema, and variable type support is there. I guess it's maybe more of a difference in philosophy than anything else, in that the HDS schema was developed as a means to support a scalable service. Whereas ZAR, the schema was the focus of the effort. Now we're at a point where I think ZAR has a lot of mind share. Would it make more sense to adapt ZAR to use HSDS than HSDS keeping its own schema? Next slide. So this is my concept of embrace and extend. So the idea would be to enable HSDS to use ZAR as an alternative storage format. We could add support for HDF5 features as ZAR extensions. And the ZAR community has a process that, a fairly robust process to submitting extensions to the ZAR spec. Performance-wise, it should work as well, HDS with ZAR, as the native storage schema. And there would not be any changes needed for client libraries like RESTful or H5PyD. What's the consequence? If you had a ZAR data store, you could access it through HSDS. So users have this ability. They can talk directly to the storage, or they use the service interface. So the direct storage is advantageous in many cases when your application is close to storage. Say I'm in the same data center as the S3 bucket. HDS service access works well. Say I'm using my notebook and I'm connecting to an HDS service in the data center through H5PyD. In that case, if I do, say, a selection, it's not every chunk for that selection has to go to my notebook. It's only the result of that selection that comes to my notebook. And depending upon what kind of selection you have, that could be a factor of 100 or more. And so together, I think rather than kind of confronting the ZAR community or saying we don't care about them, it would be kind of working together in a collaborative way to make things better for everyone. Okay, another idea is the ZAR vol connector, right? So here, again, we'd have a vol, but this vol wouldn't talk to HSDS. This talk would directly write to the ZAR storage. And again, the same set of extensions would likely be needed to support a ZAR vol connector, the same extensions to the ZAR spec. And now you have a case where HDF5 applications can utilize ZAR storage easily. You'd have the ability to use HDF5 specific features that you can't do now with either the Python ZAR package or the C library for ZAR. And ZAR vol combined with multi-threading would enable performant read-write applications. Without multi-threading, you'd have basically the same restrictions we have now with ROS3 VFD in that requests would be serialized. Okay, next slide. Okay, last idea is called H5 box, Dropbox for HDF5. So I think Dropbox is really nice, because I can have the files I care about in Dropbox, and then if I have my iPad or my notebook or my phone, it's all there. So here's the idea is to use kind of a Dropbox experience specifically for HDF5 files. So you would, and the concept would be you would define a set of files that you want to be available through H5 box. As your applications are accessing these files, they would the Dropbox service would automatically download pieces of those files as needed. You'd have a local cache so that the files you accessed yesterday, or the parts of files you accessed yesterday, would be available in your device today. And then this Dropbox H5 box in the background could be downloading data that you may need in the future. Maybe do some kind of heuristic algorithm to say, okay, I've been reading this part of the data set. I'm likely to need the rest of the data set. And you have a settings page that would allow you to set the cache size, data sources, passwords, etc. The benefit is that user would need to futz with manually figuring out where to download files from some provider. It would all just magically work. If it was a very large file, say a terabyte size file, but you're only reading specific data sets or portions of data sets in the file, you wouldn't need to download the entire terabyte. You just download parts you need. And if you move between different devices, you'd have the same view of the same set of files. All right. All right, that's it. So conclusions. There's a whole big grab bag of different ideas. The HDF group doesn't have time to do all of them. If we had people in the community who would like to collaborate on any one of these, that would be great. All the ideas need more fleshing out and more detailed spec. Ideally, we would get funded for these, so writing proposals is part of our next steps. Finally implementing them, and then kind of assessing what worked, what didn't, and so on. All right, and some links to follow up. And that's it. 15 minutes early.
Thank
So
you,
any
John.
questions? Yes.
I'll take any comments or questions from the room. If you can't hear from the microphone, I'll relay it to you through Zoom.
Okay.
Ton of feedback. Why don't you merge in the H5 ID and H5 bring them down as one code base, refactor, and have a pluggable backend that either operates locally or towards the cloud?
Right. I've been thinking about that. I don't know. It's an open question if the H5 Pi community would be on board for that. But maybe a flip way to do it would be to have H5 Pi D invoke H5 Pi as needed. So if you open a local HDF5 file through H5 Pi D, that file, you would just get a file handle from H5 Pi.
Yeah, that could be a mechanism for at least prototyping the problem question that we decide. But okay, cool. That was one thing. And the other thing, I mean, yeah, we're all, but I would probably say that given user base customers of the HDF group, I would maybe suggest making HDF4 the first target for an alternate backend
I'm sorry, I didn't. Could someone repeat the question?
I mean, that seems to be the bigger main focus for the HDF group, right? How do we get access to all the HDF4 files in the cloud? You know,
Yeah, it has been my experience. Actually, for read access, I've been thinking about it'd be fairly easy to support not only HDF4, but say a GeoTIFF or other chunk file formats, because the same trick we do support traditional HDF5 files in HSDS. Namely, we harvest the metadata and we keep pointers to all the chunks. It seems like it would be easy enough to apply, say, for GeoTIFF and do the same thing, or HDF4 files. It'd be a read-only interface, but that seems totally fine.
Yeah, HSDS will just have to be re-architected somewhat so that it has a pluggable interface for documents, which you need for ZAR anyway.
I'm sorry, what was that?
I said, you need a pluggable interface for different formats, but you need that for, so, you know, make it flexible with ahead of time to think about targeting HDF4 or geotech.
Right. And Quincy, since you're here, I was thinking about something you said the other day about sharded format, but the shards would only have the chunks, and the metadata would be in a database.
Yeah.
I actually thought about that way back when I was first starting on HSDS work, and I decided not to, primarily because I didn't want to complexify setting up HSDS. You know, like a database would be another thing that users would have to deal with. But I think it's a very reasonable thing, and I could see that as a alternative interface. So the person who sets up HSDS would have a choice of either using a database for attributes or just using what we do now, which is these JSON files. But overall, I think I want to say one more thing is that I think the time has come to really get serious about defining a sharded interface for HDF data. I think I did this for HSDS and ZAR did it for ZAR, but I would like to see some form of sharded data format actually become standard and supported both in the library and HSDS and wherever else would need that.
Yeah, totally. That's what I did as well. It's standardized for sharding, hopefully objects clearly collaborating to get it right.
Mm-hmm.
I mean, I can imagine, I already mentioned yesterday morning, you know, the interface to the metadata has to be pluggable, so I can put multiple databases behind it. But if you really wanted to, you could write a JSON backend for it as well, and not stuff it into a database and just hold it locally with a JSON driver instead of a SQLite. Okay.
Right.
Anyway,
Yeah, thanks.
things that popped into my head while I was, you know, watching you step through this one.